Hello, I'm Reagan Horton, and I am the project manager for the Process Pioneers. And in this first presentation, we will be going over how to identify the optimal vessel. Okay, so the Process Pioneers are made up of me, Reagan Horton. I am again the project manager for this presentation. And then we have Abdur Farafi, Daniel, Logan, Praneeth, and Sarah that make up the rest of the team. Okay, so first we're going to go through our executive summary of this presentation, and the project objective is to evaluate and compare multiple vessel configurations for the Texas Park and Wildlife Marine Research operations. Our goal is to find which one of these vessel configurations is most efficient and cost effective for them. And some of the key considerations we're going to be looking at is going to be the construction cost of the vessel, the operating cost, ease of maintenance / repairability, the speed, durability, as well as the operating space for the Texas Park and Wildlife crew operating on the vessel. The methodology we're going to be using to determine which one of these is the optimal fit is going to be the constraint weighted factor model, which we'll go through later, and then we will end the presentation with which vessel we have chosen based on this methodology. All right, so for our project configurations, we're looking at 4 major parameters, and those are going to be the hull size, the hull material, engine type, and cabin type. For the hull size, we're going to look at a 34-foot, a 36-foot, and a 38-foot different spec. And then for the hull material, we're looking at both fiberglass and aluminum. The engine type is always going to be diesel, but we are going to be looking at a single and a twin diesel engine. And then the cabin type is going to be a half cab or a full cabin. And the different things we're going to be looking at here to consider in this project is the bigger the boat, the more it's going to end up costing, and the more engines we're going to need to power the boat. So that's something we're going to consider in the hull size. And then the hull material. Fiberglass is cheaper and easier to maintain and to repair, but it is also more common to blistering than aluminum is. So aluminum will be more expensive, but will not blister as often. And then for the engines, we're all going to be looking at diesel, and they're going to be inboard. But the more engines that we have, the more it's going to potentially weigh, and it's going to be more reliable with more engines, but it also is going to take up more room, and we're probably going to need to get the price up higher as well. And then for the cabin, we're looking at full and a half cab, and the more cabin that we have, the more that we're going to be protecting the people working on the boat from the weather, but we're also going to be reducing their workspace, so that is something else we are going to keep in mind during this project. Here are the design factors that we're going to be considering when selecting the optimal vessel. We got the construction cost, speed, durability, operating costs, ease of maintenance, and then the operating space. Now to establish our weights and our scores for our factors, we have taken the average of all 6 members' input on what they believe are the most important factors and how they would score each one for each vessel. Here we see that the construction cost is 20%, operating cost is 25%, ease of maintenance is 15%, speed 5%, durability 10%, and operating space of 25%. Next, we look at our configuration for the factor scores of the 6 factors in our 24 different possible configurations. All 6 members were given their input on how they rated the scale of 1 to 10 on each of the following factors. We then took the average and added them to the table to ensure that we had optimal results for what we considered to be the most important factors for each configuration. Our final step in our methodology is looking at the constraints. Here for each factor, we're going to be assigning a 0 if it fails to meet the constraint and a 1 if it passes. The constraint for the construction costs is going to be if it is under $60,000 for the fiberglass or $75,000 for the aluminum. The operating cost is going to be a 1 if the fuel per trip is less than $400 and maintenance is less than $2,000 a year. The maintenance and repairability is going to be looking at how easy and affordable it is to maintain, such as fiberglass, which is easier than aluminum and can corrode, making it more difficult and expensive than fiberglass. So here we scored it a 5 out of 10. The speed is a 1 if the vessel can hit 20 knots. Durability, the aluminum is preferred for impact resistance. It's a stronger material, and fiberglass can blister. So here it is a 6 out of 10 we're assigning. And then a 1 for the operating space is if there is enough deck space for research for everyone on the vessel. Now we're going to be applying our methodology to find the optimal vessel. First, we're going to be using the applied constraint from a 0 to 1 multiplier for all the design factors, making sure that they have met the minimum criteria. Then we're going to multiply it by the scored of each vessel from 1 to 10 for all factors, then multiplied by each score by its own weight. The final score will be used as final score is equal to the summation of the constraint times the weight times the factor score for each of the configurations. The highest scoring vessel will be the optimal choice. Now that we've applied our methodology, we are now able to observe the results. Here we can see that number 15 is the highest configuration factor score with 5.66. Based on our calculation, the highest scoring vessel is the 36-foot aluminum boat with a single diesel engine and a full cabin. This vessel should be durable and can handle the tough weather, has enough space to work comfortably, and shall balance cost, maintenance, and performance. This shall be the optimal vessel for the Texas Park and Wildlife Marine Research.